In this video, we are going to look at the titration of a weak acid with a strong base. A certain number of goals here we are going to look at to accomplish in this lesson. Firstly, we're going to determine the concentration of either the acid or the base using the mole map and three-step method. So we're going to determine in this one a volume of a missing acid or base. Then what we're going to do is we're going to calculate the pH of a weak acid. Next, we're going to calculate the pH sort of a little bit into the titration. Step 4, we're going to do it at the halfway to equivalence point. Equivalence is where the moles are equal. 5, we're going to calculate the pH at the equivalence point. So we're going to go from acidic to basic. And then we're going to calculate the pH just slightly past the equivalence point. And then we're going to calculate the pH of the base, which we could do at the start of the question, but we're going to leave it at the end. We're going to create a pH graph of this titration, and the whole point, and how I've organized this video, is our pH is increasing towards 14, hence the order of what we're doing. So right off the bat here, let's take a look. We have got 30 mils, 0.2 molar HF. Now, HF is going to be our weak acid in this case. Look it up if you're not sure that it's a weak acid. And we're going to put that into the flask. Then what we're going to do is we're going to add base to it, and it has a 0.1 molar concentration. Here is our balanced equation. Everything is a 1-to-1 ratio in this one, and that'll just make the math nice and easy for us. So the first step is we're going to take the information given up here and bring it on down here, and we're going to find the moles. So 0.2 times 30, I'm going to leave this in milliliters. Our answer is going to come out in millimoles. So 6 millimoles here. Next thing we're going to do is do a little mole ratio to get the moles of NaOH. We'll bring our moles of HF down here, set up an expression. We're going to look to the balanced equation. It's a 1-1 ratio, so for every 1 mole, again there's a pretend 1 here, of HF, it's going to react with 1 mole of NaOH, and the HFs cancel out. Our number doesn't change, but now we have 6 millimoles of NaOH. So we can carry that on to the last step. Sometimes you find concentration here. This question we're going to find the volume of NaOH we're adding. So our volume is equal to N over C. N is the aforementioned 6 millimoles, and C is going to be given in the question as 0.1. And when you divide those two out, you get 60 milliliters. So this substance is neutralized at 60 milliliters. We need to remember that. So moving on here, we're going to calculate the pH of this weak acid, which is going to be done in a few steps. First thing we're going to do is write out our little ionization equation here, and we're going to put it into a rice chart. So I stands for initial. Initially, we've got a 0.2 molar solution, and we have nothing of the E other two. So the only thing that can happen here at equilibrium is a decrease for the HF, and an increase for the H, and an increase for the F minus. So putting those two expressions together into our E part of our box, we get that. Now, we are going to write our Ka expression. Why Ka? Because it's an acid. So it is going to be our products on the top over our reactants on the bottom. Products over reactants. And the other thing we need to realize is that Ka is a value we can look up. So if you look that up, 6.6 times 10 to the minus 4 is the acid constant. So let's go ahead and plug everything in. Now there's one thing that we need to remember, that this minus x is going to be so small that we can in fact ignore it. That is going to make our lives a lot simpler mathematically. So we're going to do some cross multiplying. It ends up being 6.6 times 10 to the minus 4 multiplied by the 0.4, so it's the bottom of the right-hand expression. And then I just left the top here as x times x. And when you multiply that out, it actually ends up being x squared. Again, to make our lives mathematically simpler, we're going to take the square root of both sides. Square root of x squared is in fact x. And when you take square root of 6.6 times 10 to the minus 4 times 0.2, you should get 1.14 times 10 to the minus 2. Technically, this is a molarity. What we're going to do with it, though, is we want the pH, so we're going to take the negative log of that value, and we get 1.94. And we ask ourselves, does this value fall on the pH scale in the acid range? And it sure does. And so we're going to stick with it, as 1.94 is our first number. Next thing we're going to do here is we're going to calculate the pH just before halfway to the equivalence point. So here's what we're going to do. We're going to calculate it after we've added 20 mils of base. Now remember, it takes 60 to neutralize this. We're just saying, well, what's the pH of the solution after we've added in 20? So here's our balanced equation. And what I like to do at this point is I like to figure out how many millimoles of each solution are actually present in our flask. So the first thing we're doing is we're figuring out the millimoles of the HF, and we're going to do it from these two values right here. So this might seem familiar. We get 6 millimoles. Now, how much millimoles do we got when we have 20 mils of 0.1 molar? That's the next thing. I like to do that calculation right underneath here. Multiply, multiply, we get 2 millimoles. So what's going on here is that we started with 6 millimoles. We've added in 2 millimoles of the base. Those 2 millimoles are neutralizing 2 millimoles of the acid. In essence, what's happened here is we have some unreacted HF remains, and we're just going to subtract those two values, and we get 4 millimoles. So there are 4 millimoles of this HF that is unreactive. Now, there's a minor issue though. We'll get to it in a sec. So first thing we're going to do is we're going to come up with the new concentration of the HF solution. So our concentration is NO divided by V. Now the N is what we just determined earlier to be 4 millimoles. And the total volume of our solution in the flask is 50. Where does that come from? Well, the 30 that was in there and the 20 that we added equals 50. Multiply that out or divide it out, 0.08 molar. Now, there is another wrinkle here, and that's that this NaF is being created. Now, what this NaF is made of is, of course, it's made of Na ions and F ions. Well, we don't really care about the Na ions. They are spectator ions. We're going to forget about those. But we really care about that F minus, because what that F minus is going to do is it is going to, in fact, exist and is going to participate now in our Rice chart. Because you might remember that when HF breaks down, it has some F. So here's what we're going to need to do. We need to figure out how many millimoles of this F actually exist, and the amount that exists is the amount of the NaOH that we added in. It's like, at the start there were 0 millimoles of NaOH. Then we've added in 1 millimole of NaOH. There's a neutralization. That would mean that there's 1 millimole of F being created, and it just goes up and up and up until you hit the equivalence point. So in essence here, F is just how much NaOH we've added at a certain point, and in this question we've added 2 millimoles. So we're going to take the 2 and divide it by the total volume, 50, and that's going to give us 0.04 moles per liter. Now both of these numbers are now going to appear in our Rice chart. So let's do that next. So there's our equation, there's our Rice chart, and let's fill it in. So we got 0.08 molar. That's gone down from the previous Rice chart. We've got none of that, but we've got 0.4 moles of that. So this goes down, this goes up, and that's what we have in equilibrium. So once again, we write our Ka statement. This should seem familiar. We know our Ka value. We're going to plug things in. Now the only difference here from the last time is that we've got two x's we can ignore. We're going to ignore that one. We're going to ignore that one. So it's going to make our math a little bit simpler. So all I've done is I've done one cross multiplying here. I've done the left side multiplied by, I've done that times that. Now, all we're going to do now to solve is we're just going to divide both sides by 0.04. So there's no square rooting in this version here. And we get that, and that's a concentration. We're going to do the log of that value. And when we do that, we get an answer of 2.87. We ask ourselves, is that in the acidic range on the pH scale? Of course it is. And so we're going to stick with that answer. So consider our previous pH was like 1.94. We've neutralized. It's gone closer to 7 in this case, or 2.87. Moving on. Now we're going to calculate the pH halfway to the equivalence point. So halfway, remember it took 60 to neutralize it, so it's like we're saying, well, how much is there if we add in 30? Well, this is going to be real easy, this part. All we're going to do is take the negative log of the Ka value, get 3.18, that's it. You can go through a Rice chart, yada, 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 everything's going to cancel, and you're going to be left with 6.6 times 10 to the minus 4, so that's why you can just do it at this point here. So that's our next value. Now we're going to jump up to the pH at equivalence. Now keep in mind, we could have figured out the pH after we've added 40 mils of base, 50 mils of base. It would take a while, but it would be doable. But we're going to jump right to the equivalence point here. So we have to firstly discuss what's actually present in the solution at this equivalence point. So we know this equation here. We've got that acid, it's already in our flask. And of course what we're doing is we're adding in base, and we get a couple of other ions. Now once again, we need to realize that Na is a spectator ion. We're going to get rid of that. Well, what else do we have left over? We got an H and an OH. What do those combine to make? They combine to make water. So what we're going to do now in this part is we're going to take this F minus and this H2O, and we're going to write them together like this, and we're going to put a double arrow, because what's going to happen is they are going to start to react with each other. In fact, hydrogen from this OH is going to move over here to H. It's going to make HF. And then we end up with this OH minus, and I think that should make some sense because we're adding in base. We are pushing up higher on the pH scale. So let's continue on here, and we need to do a couple things. So the first thing I like to do is talk about how much of this F minus existed. Remember earlier we were saying that it started at 0 and eventually it worked its way up to 6 millimoles. And that's exactly what we've got now, is we've got that many millimoles of the F minus that still exists because it came from the HF. We don't care about water, but we do need to figure out the new concentration of this solution. So the concentration of the solution, the N is going to be the 6 millimoles, and the V is going to be, well, the volume that is present in our flask. Remember, we started with 30 mils of acid, we added in 60 mils of base. That gives us a total volume of 90 that's in there. So that is going to be the concentration of our solution that is present. Now, since we're talking about OH here, we need to transition from talking about Ka to Kb. So here's our equation. We already know what Ka is. Kb is a constant as well. You can look that value up. Essentially, we're just dividing the two out, and we get a Kb value of 1.5 times 10 to the minus 11. Now we can continue to proceed. Now we're going to do a Rice chart. So we just figured out the concentration of the F minus, which was 0.067. We don't care about water. That has no molarity. The HF has 0, and the OH has 0. So we're going to go down, we're going to go up, we're going to go up. Those are our values at equilibrium. We're going to take our expression. Now I've changed it. It's now Kb, and again, it's equal to our products over our reactants. We don't care about water. It's not part of this. Plug your numbers in. Once again, I didn't say it, but we can ignore that x. So we're going to cross multiply and then take the square root of both sides. I've omitted that calculation, and I've just included that the final x value, 1.005 times 10 to the minus 6, and there is a big M on that. We don't really care about that because we are next going to take the log of this value, and when you get it, you have to realize, well, technically we're doing the base here, right? So it's not a pH we actually got, it's actually a pOH. So we get a pOH of 5.99. Now we're more interested in pH because we are doing a pH graph. So we are going to take 14, subtract our answer, and essentially we have a pH of 8. So what we've discovered here is that the equivalence point with a strong acid, with a weak acid and a strong base, our pH is actually above 7 now. So the strong base makes it above 7. Let's continue. Next thing here, we're going to do the pH slightly past the equivalence point. So all I've said here is that we've added 65 mils of the base in. Now remember, it took 60 to neutralize it. In essence, we've got 5 extra mils. So in those 5 extra mils, all we need to do is calculate how many millimoles of the NaOH are actually present. So remember, our concentration is 0.1, and our volume is 5. That's the 5 extra we've gone past here, all right? Didn't know how to word this one, but that's what I went with. So you multiply those out, you get 0.5 millimoles of the solution. So we've got 0.5 millimoles divided by our total volume of 95. Again, that's 65 and 30 added together. That's the concentration of our ion here. This is basic, remember. So we do the negative log of this value. You get 2.28, which, again, doesn't make any sense because we're talking about a base in this case. I didn't really do this on the last slide. But that's the rationale, and so we need to subtract here, and then we get an answer of 11.27, and that, again, should make sense. Our previous pH was 8, we added some more base in, it's going higher towards 14. The last thing we can do now is we can calculate the pH of the base, and we could have done this right off the bat because we knew the concentration of the base. It's a strong base, which means we can just go straight ahead and do the negative log of the 0.1, and we get an answer of 1. Does that fall in the basic range? Obviously not. So we need to go 14 minus our answer, and we get an answer of 13. Now that we have all these values, we can create a titration graph. So here we go. On the bottom, we've got our volume of NaOH added, and up the side here, we've got pH. So the very first thing we did was we had no base added, and our pH was like 1.94. So there's our first dot. Then we added in 20 mils of base, and the pH increased a little bit, 2.87. Next thing we did was we did at the halfway to equivalence, which was 30 mils of base, and it was 3.18. Then we jumped all the way up to 60, and that's where our equivalence point happened at 8. And then we did a couple other points. We had that one and that one. So we can make a graph here. And again, we've got a range here where we didn't really have anything. We could have figured those out. But the point is that we've got an increase. It's going to steadily go. And then once it gets here, it's going to increase quite a bit. And then it's going to go off, and it's never really actually going to get to that last thing of 13 because it's always going to be slightly diluted, so it should be slightly under that point. Our buffer range is kind of happening in here. Again, it's plus or minus, but it should be plus or minus 3.18, and the buffer range is where your solution doesn't change. And that is the end of that.